Hello students, now we will be talking about motional EMF. What do you mean by motional EMF? Simply taking the first word, that is motional, means motion. A motion of a conductor that will create an EMF. So whenever there is a conductor moving inside a magnetic field, there will be EMF induced inside it. So that conductor will behave as a battery when it is moving inside a magnetic field. So we'll find the EMF that is produced due to motion of conductor. We can find it by two methods. One is Lorentz force and one is by using Faraday's law. In your NCERT textbook it is only given by Faraday's law, but we'll try to understand it with Lorentz force also. So first of all we'll start with Lorentz force. Suppose there is a magnetic field that is going inside, and there is a conductor we have kept over here. A conductor with length L. A conductor whose length is L. It is kept inside the magnetic field. Now, if it is in stationary motion, the flux inside it will be constant, so there will be no induced EMF. But if it starts moving, if there is a motion, we give it a motion with velocity v, then what will happen? It will continuously cut the flux. So there will be EMF induced inside the conductor. So how it works now? Suppose we know that using Lorentz force there will be force inside a conductor. We know there are many free electrons inside a conductor. There are number of free electrons inside a conductor. So when this conductor will move, the electrons will also move in the direction. And we know by there is a force on any charged particle whenever it is moving inside a magnetic field by using Lorentz force. So if I put the fingers of my right hand in the direction of magnetic field, that is going inside, the direction of the thumb should be in the direction of positive charge. The direction of thumb should be in the direction of positive charge. Here it is electron, so negative charge. So ultimately what we can do, as it is not positive, it is negative charge, ultimately we can change the direction of force. So first we will find the direction of actual force. This is the direction of magnetic field, this is the direction of velocity, then my palm will show the direction of magnetic force. Direction of magnetic field, direction of velocity, and the force will be showed by the direction of my palm. So what is the force? Direction of force is in this direction. But we are having the negative charge instead of positive charge. We have already very specifically said in Lorentz force, while studying Lorentz force, that this thumb should show the direction of or the velocity of positive charge only, but here it is negative charge, so we'll reverse the direction of force. So the force will be in downward direction. We can say that magnetic force on an electron, because it is negative charge, the direction of force on electron will be in downward direction. That will be magnetic force. So we can write that Fm. What is the formula for magnetic force acting on a moving charge? It will be Q V cross B. If anyone doesn't know, please move towards the previous lecture and find out the formula. Okay. So what happens after some time when the conductor moves over here? Electrons are getting collected in the downward direction. So here what happens? The negative charge is getting accumulated. Similarly, if the charge on electron is in downward direction, we have seen that there will be charge on positive ions also, and positive ions would be collected in the upward direction. Here it will be collected in upward direction. So here you can see there is a potential difference created between this, and also an electric field is generated. Electric field is from positive to negative. There will be an electric force, or you can say electric field generated inside it. So this will act as a battery, as there is potential difference created between two. Now after a certain time what will happen? As the accumulation of charge increases, in lower direction, at the bottom part there is negative charge and in the top part there is positive charge. So after some time, as the electric field increases, what will happen? This positive charge will try to attract this electron. This positive charge will try to attract the electron towards its side. So what will happen? This electron will face an electric force in the direction opposite to the magnetic force. This will be Fe. Okay, can you understand once again? Initially there was no electric force, so what was happening? The magnetic force was pulling the electron in the downward direction, but after some time the electric field also got increased. Due to that, the charges also got accumulated, positive charges. So what will do? Positive charges will try to attract the electron towards it. So there will be an electric force in the opposite direction on the electron. So by how can I give the force on electron? It will be Q into E. Can I write it in this manner? In both places I can write, instead of Q I can write E, that is for electron. So here I can write E V cross B, and here I can write E into E. I hope this much is very clear to you all. Now at certain point of time what will happen? The amount of magnetic force that is acting downward will be equal to amount of electric force that is acting upwards. Means both the forces will be acting in opposite direction, and this is known as steady state. At certain point of time Fm will be equals to Fe. Fm will be equals to Fe. Why I have kept it in modulus? Because both are in opposite direction, but the magnitude of both are same. So if you remove from modulus, you need to write it in this manner: Fm equals to minus Fe, or you can write Fe equals to minus Fm, either or, because the direction of both the forces is opposite. Electric force is acting in upward direction, whereas magnetic force is acting in downward direction. But at steady state condition, both the forces will be equal. So if I write from here, I can write E V cross B is equals to minus E into E. From here I can cancel out E. Okay. So V cross B is equals to E. Okay. Now we know that potential difference is equals to E dot L. Potential difference is equals to E dot L, where L is the length of the conductor, or you can say the distance between the two different charges. You already studied this in your fourth chapter. Delta V is equals to E dot dx. You have studied this. Delta V is equals to E dot dx. This is the same thing, where dx was the distance between the charges. Here also L is the distance between the charges, E is the electric field, and delta V is the potential difference that is created. So can I put the value of E from over here? E will be equal to delta V by L. So if I put the value of V over here, I can write V cross B is equals to minus V by L. Okay. So I'll take this L over here. So I'll write it in this manner. Okay. Now what is the potential difference? Here the potential difference is equal to the EMF that is produced. So EMF will be equal to, I'll take this negative sign on the other side, will be equal to V cross B dot L. Here I can put negative sign. Okay. Is it clear? Now this is a very generalized form. This is the generalized form of producing the EMF. Now you can solve it further also for this condition. For this particular condition, what is V cross B? V is in this direction, B is in the inward direction. The angle between two is 90 degree. So if I try to solve it, it will be E equals to VB sin theta, and theta will be 90 degree. Okay, into L. So it will be equal to VBL. Okay, it will be VBL, or you can say minus VBL because of the minus sign. So the induced EMF produced, in this thing will be E equals to minus VBL. That will be the induced EMF produced inside this conductor. Whenever the conductor is moving, at that time the EMF of this will be induced. As soon as the conductor stops moving, this EMF will be removed. It is only possible if the conductor keeps on moving. Okay, I hope this is very clear to you. Then we'll move towards the Faraday's law. What happens in Faraday's law? Suppose we again have a magnetic field. Suppose we have a magnetic field. We'll take a rails. Okay, these are rails on which a conductor can slide. These are the rails on which the conductor can slide. Suppose we put a conductor over here. Suppose we put a conductor over here whose length is L. Okay, the length is L. Now if we push this conductor in this direction with velocity V, what will happen? The area inside this frame will increase as this will move. This is a sliding conductor, so the sliding conductor will move in this direction. If we apply the velocity, it can move in this direction also, and you can prove it with using this direction also. Both are one and the same. What is required for induced EMF? That is change in area. Change in area. A fixed area is not required. So either you can push it in this direction also, either you can push it in this direction also. Okay, just now we are taking this direction. If you want to prove from this direction, you can prove for that also. Okay, so after some time, suppose say after some time dt, what will happen? The frame will reach at this position. The frame will reach at this position. So what will be the distance? It will cover the distance dx. It will cover the distance dx in time dt. So if I write what is the change in area? Change in area. Change in area dA will be equal to, what is change? This is normal area, so I am not using. If you want to write anything over here, you can write this also. Suppose say P or anything. But we are only concerned in change in area, because a fixed area cannot produce induced EMF. Only the change in area will produce the induced EMF. So if I want to write change in area will be equal to length into this distance, that is the change in area. So I can write L into dx. Can I write it in this form? Yes. So this is my change in area. Now what will the flux? Total flux inside this area would be equal to B dot A, or if I want to remove this dot product, I can write BA cos theta. What will be the cos theta? The angle between B and A. What is my direction of B? It is going inward. It is going inward to the board. What will be the direction of A? Area vector is always perpendicular to the area, which means that it will also be in inward direction. If I am having, this is my plane, then what will be the direction of area vector? Area vector, either it would be inside, either it would be outside. We can take any of the thing. Both the side it is correct. Suppose it is inside or it is outside. Both are correct. So here we'll consider as it is going inside. If we are taking outside, then we'll have only a negative sign. Okay. So here we are considering it is both the things are going inside. Magnetic field is also going inside, and the area vector is also going inside. So the angle between them will be equal to 0. BA cos 0, which will be equals to BA cos 0 is 1. Okay. I hope this much is very clear to you. So now the change in flux for this small area. If you want to find the change in flux, then we can write d phi. D phi will be equal to d BA. But here magnetic field is constant, so I can remove it outside. Will be equals to B dA. Okay. I hope this much is very clear to you. There is no issues in understanding this. Now what we'll do, we'll write EMF according to Faraday's law. What is induced EMF according to Faraday's law? It is the rate of change of flux with respect to time. Rate of change of flux with respect to time, and the direction of that induced EMF is in the direction opposite to the force that is producing it. So we put a negative sign over here. So from here, if I put the values, from here we have moved over here. E is equals to, what is the value of d phi? It is B dA minus of B dA upon dt. Okay, can I write it in this manner? So if I put the value of dA now, what is the value of dA? Minus B L dx whole divided by dt. Now if we look at a single term, that is this. If you look at this single term, what is it? Distance traveled upon time taken. Distance traveled upon time taken. Where shall I write it? Okay, here I will write it. Dx upon dt. Distance traveled upon time taken. Will it be equal to velocity? Will it be equal to v? What is v? V is velocity. Velocity is distance traveled per unit time or the time taken to travel a particular distance. So instead of this I can put the value of V. Then E will be equals to minus BLV, and this will be the induced EMF inside the conductor. Here you can see both the values are same. BLV, BLV. Induced EMF is equals to negative of BLV. Okay, that is due to the Lenz's law. Okay, due to that force the direction is opposite. So I hope this is very clear to you. This will act as a battery. Here there is a huge amount of potential difference created. So if you connect this with a wire, okay, then this will act as a battery, because there is a potential difference, positive charges and negative charges are collected on both the ends of this thing. This is a very general formula. This formula is generally for the case where all three are mutually perpendicular. The magnetic field, the velocity and the length vector. Suppose here the magnetic field is in this direction, okay, that is inward, velocity is in this direction and length is in upward direction. Means all three are mutually perpendicular. Mostly in 80% of cases you are asked about this only, but in case if you are not asked about this, and if the length of conductor or the conductor is at some angle theta, at that time you need to use this formula. This is more generalized formula. Okay, I hope this is very clear to you. So students, keep studying. Have a nice day. Thank you.